and this is the 5th and final challenge of the buffer overflow series, and it's called Executable. So, going right in, we can see there's no free win function anymore. What will we do? This time, you'll have to write a win function yourself with raw machine code. That's badass. Hint, the stack is executable. You can use your input execute code. Look up shellcode to pop a shell. You don't need to write this yourself. Later on, we have more time. You should do it for fun, though. Hint, the address of the address is printed at the beginning of the program and is static, aka ASLR is disabled. Finally, here's some code that has been used in all of them that helps a lot. So I'm going to look at the challenge, and we'll figure out what's going on here. So if you look at execstack, it's like every other challenge, except now it becomes a little bit harder. You see, if we scroll through this, there's no print flag function anymore. It's exactly the same as the previous challenge, where we control the, where we can corrupt the saved instruction pointer, so that when we return here, we control the execution flow. Except there's no way for us to just simply print the flag out. So we have to write our own code to do that ourselves. And that's pretty fun. This doesn't really seem possible, and modern computers in a lot of ways make this impossible. A standard protection now is what is called the non-executable bit, meaning that that code is either readable and writable or readable and executable. You never have code that's readable, writable, and executable at the same time. This makes it impossible for attacks where you do get a buffer overflow to just simply execute your own code. There are ways around that called ROP and other methods, but NX was a very impactful mitigation at the time, and it was really cutting edge. But we can disable that, which is fun. So in this program, we disabled the non-executable bit so that we can execute code or a string that we wrote to this. Cool, so if we go back here, it's called shellcode. I don't really know why it's called shellcode, because we pop a shell, I guess. But in reality, we're going to write raw machine code in order to do this. So everything is exactly the same as we did before. So we can just copy and start with that. Now there is one slight difference in this one than the previous one. It has to do with some weird Unixy things. Notice here that we have the cat dash, and this is really important because once we send this data in and we want to pop a shell, we want to make sure that we're actually going to get the data out that we want. That's a really important thing. If we just ran this, then our shell would stop. So by doing the cat dash here within these parentheses, it's waiting for more user input. In the previous challenge, we learned that this was 36. This is because, just from empirical testing, I don't really have much else to tell you. We learned it was 48, not 36. It was hex 30, yeah. One structure was 32 bytes, and then 4 bytes, another 4 bytes for EBP, and then you're probably hitting the instruction pointer after that. That'd be my guess. So if you did this before, it seg faults. And this is because we sent our malicious data in there. I added the new line in there, so it just sends it automatically. But that's how this works. So we can do the same thing with XXD as before, where we're printing the information that we need to print. Except this time we need to write the shellcode, and that's the real magic of it. So instead of sending a bunch of A's, we're now going to put the machine code we want to write in there. And I'm not making a big deal of machine code for this. writing the machine code is kind of hard, and I think it's really worthwhile doing. But I think for a short CTF like this, doesn't really make sense to do. But for your enjoyment, I will explain it anyway. So this is my explanation of the shellcode that I used for this, and I just copied it from the internet right here. I would just recommend saying, hey, look up shellcode for x86 and try it. And most of them on the Shellstorm website are just going to work. What the shellcode actually does, though, is we're XORing EX with EX. In reality, this is just cleaning EX to be null. In our shellcode, we can't have null bytes or new lines. And if we're going to set EAX to be 0, then that would include a null byte. But XORing EX with EAX, if you XOR anything with itself, it's always going to be 0. So this sets the register EX to be 0. But why are we even setting EX to be 0? We are making a raw interrupt, which is going to tell the kernel to execute a program for us. With interrupts on x86, the hex 80 interrupt is a syscall. And all we're doing here with moving values and pushing registers is just setting up the syscall to work correctly in assembly. Now, we are pushing the program bin shell to the stack. And then after we do that, we're moving it into EBX. We're then going to push a null byte. And the reason we push a null byte is because we want this string to end. So we're doing bin shell null byte right at the end of it. At that point, we specify the path to execution, which is literally just going to be the same as this stack pointer, which is all the EBX really is anyway. Then we're going to execute the 0B or 11 syscall, and the 11 syscall is literally just run this program for me, execv. But I literally just copied this from this website, so no big deal. You can see here that this shell code is 23 bytes. Fun. Oh, whoops, sorry. This shell code is 23 bytes. So I'm going to copy this once. Actually, how did I do it here? Cool. I'm just going to copy this because I'm lazy, but I think I can. It's easy to explain. So here, I just copied that shellcode raw from what I pointed it to. And then we are adding in a particular amount of A's. So what we're doing is we're doing minus 23 because of the shellcode we have set up here, adding 32 for the length of our string, 4 for the integer, and then another 12 bytes for whatever's after that. And then finally, we have the actual address that we're going to use. So that actual address kind of depends. So if we do on the setup, so we have exec stack, and on this setup, we need to change this slightly. So exec stack. So we have FF, D6, and this is going to be 3C. We run it. Cool, and it works. We know it works because we are now in this program. If I run who am I, you notice that we are the next user up. So previously, when I couldn't print the flag, I now can. Now, this is the quintessential buffer overflow. We are overflowing the buffer, editing the return address, and jumping to our shellcode. This is a great day in history that you now learn how to do this. And even though this seems outdated, we had to remove a bunch of protections, we still find this. There was a DEF CON talk about how all NFC card readers used on ATMs, card scanners, and various other things were vulnerable to this exact same attack that we're doing. So even though this feels old, this is where you start, and this stuff does still exist today. To recap, we we have a buffer overflow that allows us to edit the return address. We are then, instead of jumping to the print flag function, we are jumping to an address on the stack, which contains the code that we want to execute. So we just wrote code live into the program, which is super sick. And this code is just using for popping a shell or starting the program bin bash. And although you can write this together, we just copied it from somewhere. Cool. Thanks for listening. Have a good time.